Okay, so let's pick up with diving into more detail into glycolysis. So in the last lecture, we went through the cycle from front to back and got a good overview of what glycolysis was about. But let's jump in and start adding some detail to this, including both chemical rationale and biological rationale for these steps, and talking about energetics, and eventually, near the end of this, getting to a discussion of regulation. So the first step, remember, is the conversion of D-glucose to D-glucose 6-phosphate. And to refresh, that looks like this, where we have D-glucose getting converted to D-glucose 6-phosphate via the investment of ATP being regulated or potentiated by hexokinase/glucokinase. So we're going to have an investment of ATP, in the presence of magnesium, going to ADP, and this is going to happen through the enzyme hexokinase or glucokinase, depending on the isoform of the enzyme. And what's going to happen is the 6 carbon will become phosphorylated. And remember, the the P with the circle around it stands for PO3 with a 2 negative charge on it, so that is charged. Remember, this equals PO3 2 minus. That is not enough. Let me rewrite that. That's a little ugly. There we go. And everything else stays the same. The hydroxyls stay in the same locations. And we'll just put our hydrogens in. And this, first, remember, is D-glucose. And the second one is D-glucose 6-phosphate, or G6P. So this is our first step of glycolysis. And there's a couple considerations that we should get into. So remember, hexokinase, glucokinase are both kinase enzymes, and kinases are enzymes that transfer phosphates from ATP to nucleophilic acceptors. Phosphorylation activates glucose for the subsequent reaction in the pathway. However, the formation of such a phosphoester is thermodynamically unfavorable and requires energy input to move in a forward direction of reaction. So that energy in this particular case comes from ATP. And this initially seems counterproductive, but it's a really important investment step. So glycolysis is ultimately designed to make ATP, not consume it. However, the hexokinase is one of the 2 priming reactions. So I'm going to write that in here specifically. This is a priming reaction, requires ATP investment. So recall that for the overall reaction, because we have 2 priming reactions, each which requires 1 equivalent of ATP, that per glucose molecule, glycolysis requires the investment of 2 ATP molecules, but will get 4 ATP molecules produced. Therefore, netting 2 ATP molecules per glucose. Now, in terms of the energetics of this is not a favorable reaction. However, when coupled to ATP, it is favorable. And what this looks like is if we have D-glucose plus ATP as a coupled reaction, you go into D-glucose 6-phosphate plus ADP plus a free proton. The hydrolysis of ATP, remember, is worth 30.5 kilojoules per mole, which has become available for this reaction. And the phosphorylation of glucose costs 13.8 kilojoules per mole. So when you couple these, you have a net negative 16.7 kilojoules per mole, which is a favorable coupled reaction. Now remember, this value of 16.7 kilojoules per mole is under standard state conditions, which is under 1 molar concentrations, which isn't biologically relevant. And under those conditions, the equilibrium for this reaction is going to be very far to the right. KQ is going to be about 850. But under cellular conditions, the first reaction of glycolysis is even more favorable than under standard state, where delta G is actually going to be closer to negative 33.9 kilojoules per mole. So under biologically realistic concentrations, this is even substantially more favorable than under standard state conditions. So one of the trends you're going to see over and over and over in these lectures is I'm going to lean on 2 types of rationale. I'm going to try to find chemical rationale and biological rationale for the biochemistry that we're observing or learning about. I think it's really important to keep these discrete arguments because, as you'll see, I think both contribute towards the rationale as completion of these systems and why they work the way they do. So we can see chemically why this coupled reaction is favorable, but biologically, what's the rationale? What are the cellular advantages of phosphorylating glucose? Well, the incorporation of a phosphate into glucose in this reaction is important for a few reasons. First, phosphorylation keeps the substrate in the cell. Remember, phosphates are charged. Glucose is a neutral molecule and can diffuse across the cell membrane, but once it's phosphorylated, there's a negative charge on the glucose, and the plasma membrane is essentially impermeable to glucose 6-phosphate. Additionally, rapid conversion of glucose to glucose 6-phosphate keeps the intracellular concentration of glucose low, which favors facilitating diffusion of glucose into the cell. And we know that if we are trying to make glucose into ATP, we want glucose going into those cells. Finally, this allows regulatory control to be imposed. Because this reaction is only highly favorable when coupled to ATP, that makes the first reaction in glycolysis an important site of regulation. Whenever you see an investment, a major energetic investment, like an equivalent of ATP, it's very likely that that's an important point of regulation for a process. And this isn't a great example of that. So remember, we want to have control over critical biological processes particularly those which are associated with primary metabolism. And if we had a reaction that was favorable without the coupling of ATP, it would go off without the ability to regulate it. We couldn't turn it on and off. However, now that we coupled a non-favorable reaction to ATP hydrolysis, making it net favorable, and this is being orchestrated by the enzyme hexokinase glucokinase, and we can regulate the activity of that enzyme, we now have the ability to exert fine control over our primary metabolic pathways. So you may be wondering at this point, why do I keep saying hexokinase glucokinase? Well, let's talk about the isozymes of hexokinase. And this will actually afford another layer of control that's tissue specific to glycolysis. So in most animals, plants, microbial cells, the enzyme responsible for phosphorylating glucose is hexokinase, and it's magnesium dependent, which is why you see the requirement of magnesium next to ATP in the rationale of the pathway. So there are 4 isozymes of hexokinase in most animal tissues. Hexokinase 1 is the principal form in the brain. Hexokinase in skeletal muscle is a combination of types 1 and 2. And that occurs in approximately a 75-25 ratio. The Km for glucose is about 0.03 millimolar for type 1 and about 0.3 millimolar for type 2. So let me write that down really fast. For type 1, the Km is 0.03 millimolar concentration of glucose, and for type 2, the Km is an order of magnitude greater. Therefore, hexokinase operates efficiently at normal blood glucose levels of about 4 millimolar or so, in that zone. This also means that the brain, which predominantly has type 1 isozyme, has a higher affinity for glucose with its hexokinase than the combination of muscles, which is predominantly 1 and 2. And that makes sense because if you were in a tug of war for glucose in the bloodstream, you would want the neurons to be prioritized, despite the muscles being very important as well. Now, in terms of regulation, animal isozymes, which are the ones we're primarily interested in, are all allosterically inhibited by the product glucose 6-phosphate. Which makes sense, because if we've accrued enough glucose 6-phosphate, we wouldn't see a downregulation of the enzyme activity. And this downregulation is going to continue until the glucose 6-phosphate has been decreased by subsequent steps of glycolysis, justifying the production of more glucose 6-phosphate. Now, I did mention there's 4 isozymes. Type 4 isozyme of hexokinase is called glucokinase. This is your glucokinase, and it is highly specific to D-glucose. It has a much higher Km than the others, about a 10 millimolar Km, and it's not product inhibited. And where is this found? It's found almost entirely in the liver and in the pancreas. Now, you may be wondering, why do we have such unique form, particularly in the liver? Well, with a Km of 10 millimolar, it's going to have a lower affinity for binding initially. So only under higher levels of glucose will the glucokinase start to interact with glucose. And once it's phosphorylated, it's overwhelmingly going to store that glucose 6-phosphate in the form of glycogen in the liver. So it's actually going to be used as a mechanism of subsequent storage versus primarily energy production, which is why you want to have the muscles and the nervous system tissues get the first crack at that blood glucose through these more sensitive Michaelis-Menten constants. So quick review. Let me zoom down here. For the first step of glycolysis, you can see that glucose gets converted through to glucose 6-phosphate via hexokinase or glucokinase, and this requires a priming or coupling with an equivalent of ATP in the presence of magnesium. And why is this critical biologically? It keeps the glucose in the cells through the phosphorylation, the acquisition of that charge so they can't diffuse. It favors the subsequent diffusion of more glucose into the cell by consuming the glucose and transition into glucose 6-phosphate, and it is an essential step of regulation which gives us control over the system and control over initialization of glycolysis. So, that said, let's transition to the second step of the reaction. So the second step of glycolysis is the conversion of glucose 6-phosphate to the fructose 6-phosphate. And that looks like this, just as a reminder. So we've got our glucose 6-phosphate. Oh my goodness, I'm dragging things all over the place here. Let's see if I can fix this. And once we have our glucose 6-phosphate, we're going to convert to fructose 6-phosphate. I don't know why I keep dragging this around on you guys. Sorry for the distraction. And we have a hydrogen here. Okay. Here we go. And this is our fructose 6-phosphate. And this is going to be executed by phosphoglucoisomerase. Now, if you look at this compounds, all we've done is rearranged bonds. We haven't changed the number of atoms, the number of electrons. There's been no oxidation. There's been no reductions. So energetically, these are very, very similar. And the second step is a common type of metabolic reaction. It's an isomerization of a sugar. In this particular case, the carbonyl oxygen of the glucose 6-phosphate is going to be shifted from C1 to C2. That's all we're doing. This amounts to an isomerization of an aldose to a ketose, which is our fructose 6-phosphate. And the reaction is necessary for two reasons. Firstly, the next step in glycolysis is going to be the phosphorylation at C1, and the hemiacetal hydroxyl of glucose would be more difficult to phosphorylate than a simple primary hydroxyl. So if we're looking at this hydroxyl would be substantially harder to phosphorylate than this primary hydroxyl, which is much easier to phosphorylate. So in terms of investment of energy, it makes a lot of sense that we move this hydroxyl over prior to the phosphorylation in the next step. Secondly, the isomerization of fructose activates C3, facilitating the carbon-carbon bond cleavage in the fourth step of glycolysis. So let's see here. Here's a 1, 2, 3, and we're going to be cleaving here. So destabilizing that position is going to be very important in terms of the chemical rationale for getting to where we need to go with the least amount of energy invested to do so. Yeah, put that back in there. Sorry, guys. So speaking of energy, what's this reaction look like? Delta G, under standard state conditions, is 1.67 kilojoules per mole. And under biological conditions, it's about negative 2.9 kilojoules per mole. Either way, both of these are operating near equilibrium conditions. And under biological conditions, just slightly on the favorable side of equilibrium conditions. So not only is it operating near equilibrium, it's readily reversible. So phosphoglucoisomerase proceeds through an ene-diol intermediate, which I'm tempted to show you guys here. So although we typically look at glucose and fructose as cyclic compounds, the isomerase actually interconverts them to the open chain forms that we see when we introduce carbohydrate structures, and then allows them to reform in a 5-membered ring versus a 6-membered ring. But in the sake of saving a little bit of time here, I think I'd recommend taking a look at this mechanism. It's figure 18.8 in your text, and it's a fairly simple example of a base abstracting a proton, pushing electrons to the anomeric carbon, which allows for a ring opening event, which allows for a subsequent ring closure event under a different form, where you have a different nucleophilic attack than you did with the glucose. So worth a look in the textbook, but not something I'm going to have you guys memorize. This takes us to our third step in glycolysis, which is our second primary reaction, and it's going to be the reaction of fructose 6-phosphate to fructose 1,6-bisphosphate, which is going to go through the enzyme phosphofructokinase. So what's this look like? We have our fructose 6-phosphate. And we're going to have another priming step, which involves the investment of ATP, donating as phosphate, forming ADP, and this is also going to require the presence of magnesium. And the enzyme is going to be phosphofructokinase. And we've already talked about the rationale for this, so let's just put that phosphate on there and make our fructose 1,6-bisphosphate. Eventually, I'm going to figure out how to draw on this without my hand moving the tablet around. Oh! There's our second phosphate. This is ridiculous. I'm sorry, guys. Probably just trying to go a little bit fast, like I'm moving on a whiteboard. And this is our fructose 1,6-bisphosphate. So, as a hint, because I'm drawing these by hand as I'm speaking, there's time for you guys to do the same. And as a strategy for studying and getting comfortable with these structures, I would draw along as we go. I know that it's a little bit tedious, but it helps reinforce what you're seeing to actually tactilely reproduce it. And because all of the evaluations we're doing in class require you to physically draw these structures, it's just really good habits to start drawing with me as we go. I'm moving at a pace which really facilitates that, so that's my recommendation. So like in the first reaction with hexokinase, the phosphorylation of fructose 6-phosphate is a priming reaction and it's endergonic. So if we look at fructose 6-phosphate plus an additional phosphate without ATP going to fructose 1,6-bisphosphate, the delta G under standard conditions for that is going to be 16.3 kilojoules per mole. So it's not going to be favorable. And it's therefore not going to proceed without the coupling of ATP as a priming reaction. But remember that ATP brings about 35 kilojoules per mole and change to the party. So if we couple this to ATP, versus just inorganic phosphate, producing ADP, this process coupled is got a negative 14.2 kilojoules per mole. And in erythrocytes or under biological conditions, that's closer to about 18.8, negative 18.8 kilojoules per mole, so even more favorable than under standard conditions. A lot of the same rationale applies here in terms of why we need these controls. One, it's an important metabolic checkpoint which gives our ability to control reaction, but you might think, but we already have exerted control over the first point of reaction. What's the value in this third point of the reaction? Just as hexokinase reaction commits the cells to taking up glucose, because once they've been phosphorylated, it's retained in the cell, phosphofructokinase reaction commits the cell to metabolizing glucose rather than converting it to another sugar or storing it. So, let me reiterate that. This step with phosphofructokinase commits the cell to metabolizate. Commits to metabolizing glucose versus converting to a different sugar or storing it. Similarly, just as a large free energy change of the hexokinase reaction makes it a likely candidate for regulation, so the phosphofructo reaction is an important site of regulation as well. And in fact, it might be the most single important site of regulation of the glycolytic pathway. So let's talk a little bit more about this regulation. Actually, first I should write that down. important point of regulation. Let's make a little bit of room here. So it's actually the case that phosphofructokinase is the valve which controls the rate of glycolysis because of all of the important components of regulation associated with it. So in addition to its role as a substrate, ATP is also an allosteric inhibitor of the enzyme. So ATP is both a substrate and allosteric inhibitor. Therefore, phosphofructokinase has two distinct binding sites for ATP. It has a high affinity substrate binding site and a low affinity regulatory site. In the presence of high ATP concentrations, phosphofructokinase behaves cooperatively. Plots of enzyme activity versus fructose 6-phosphate are sigmoidal, and the Michaelis-Menten constant Km for fructose 6-phosphate is increased. So when ATP levels are sufficiently high in the cytosol, glycolysis effectively turns off. Under most cellular conditions, however, the ATP concentrations don't vary over a very large range. The ATP concentration in muscle during vigorous exercise, for example, is only about 10% lower than during the resting state. So the rate of glycolysis varies much more than the level of ATP. Based on these observations, a large range of glycolytic rates cannot be directly accounted for only by these 10% changes in ATP levels. So what other factors are associated with regulating phosphofructokinase activity? Well, AMP is another one. AMP reverses the inhibition due to ATP, and AMP levels in cells can rise dramatically when ATP levels decrease due to the action of enzyme adenyl cyclase, which catalyzes the reaction. So we know that ADP plus ADP can reversibly convert to ATP plus AMP via the reaction adenylate cyclase. And the presence of that AMP reverses inhibition due to ATP. So clearly, the activity of phosphofructokinase depends on both ATP and AMP levels and is a function of cellular energy status. And we're going to keep coming back to this concept of cellular energy status helping to dictate primary metabolism. So phosphofructokinase activity is increased when the energy status falls and is decreased when the energy status is high, meaning when the cell needs more energy, it turns up. When it has lots of available energy, it turns it down. So the rate of glycolytic activity decreases when ATP is plentiful and increases when more ATP is needed. Makes sense. Now, one final point, glycolysis is actually coupled to the citric acid cycle, or TCA cycle, which we're going to be describing in the next chapter. And they're coupled via phosphofructokinase, because citrate, which is an intermediate of the citric acid cycle, is an allosteric inhibitor of phosphofructokinase. And this ties the TCA cycle directly to the regulation of glycolysis. I said last point, but I fibbed. Additionally, phosphofructokinase is regulated by beta-D-glucose 2,6-bisphosphate, which is a potent allosteric activator that increases the affinity of phosphofructokinase for the substrate fructose-6-phosphate. That's one more that we should account for here. So beta-D-fructose 2,6-bisphosphate. And it's a allosteric activator, particularly potent one. Okay, so let's zoom back. Oh, over-zoomed. Drag this here. And do a quick review of our third step. Fructose-6-phosphate goes to fructose 1,6-bisphosphate via the investment of ATP and the action of the enzyme phosphofructokinase. And once coupled to ATP, it's energetically favorable, but in the absence of ATP, it is not energetically favorable. This step is incredibly important because it commits the glucose to being metabolized for energy compared to being utilized for storage or for being converted to some other carbohydrate. And it's an essential point of regulation for all of glycolysis. It's regulated by ATP. So ATP is both a substrate and an allosteric inhibitor. It is regulated by AMP, which reversibly reverses the inhibition of ATP, and is also tied to the TCA cycle via citrate, which is an allosteric inhibitor, and is additionally allosterically activated by beta-D-fructose 2,6-bisphosphate. So, with that, let's move on to reaction 4, the cleavage of fructose bisphosphate to form 2,3-carbon intermediates. Now, in the last lecture, I mentioned in the overall description of glycolysis that in the first phase, what we're really doing is we're investing 2 ATP so that we can modify the structure of glucose chemically to give it a pair of phosphates with a pseudosymmetry so that we can divide it from a 6-carbon carbohydrate into a pair of trioses, which can then be isomerized to a pair of identical trioses that feed into the second phase. And that's what we've just reached. We've reached the step now where we're going to cleave the fructose bisphosphate into a pair of trioses, dihydroxyacetone phosphate and diglyceraldehyde 3-phosphate. And this is what it looks like. So first, I'm going to draw the fructose 1,6-bisphosphate. In its cyclic form. And then I'm going to show it in its linear form because these can reversibly undergo ring opening reactions, which we learned when we looked at carbohydrates in the first semester. And although they're not preferred in that form, because these are mediated by enzymes, this will give us some insight into the mechanism by which this is cleaved. Our fructose 1,6-bisphosphate is going to, I should actually have that, let me reversibly open into a linear form. And here we have the ring open form of fructose 1,6-bisphosphate. Now, this is going to undergo aldol cleavage at between the third and fourth carbon. And you may remember the aldol reaction from organic chemistry. It's just an aldol cleavage is the opposite, a reversible reaction of the aldol condensation. And all we're seeing here is a reversible reaction being exerted by fructose bisphosphate aldolase enzyme. Make a little bit of room here. And following the cleavage, we're going to end up with the following. Let's see if I can get rid of that. And here I am exploring new technologies and encountering occasional difficulties with using the tablet, but let's make it so. So the first of these are dihydroxyacetone phosphate. Dihydroxyacetone phosphate. Remember, looks like an acetone with a pair of hydroxyls, but one of them has been modified with phosphate, hence the name dihydroxyacetone phosphate. And our other molecule is our glyceraldehyde 3-phosphate, which is going to have an aldehyde, glyceraldehyde, modified by phosphate on the 3 carbon. So glyceraldehyde 3-phosphate. Now, energetically, this reaction has an equilibrium constant of approximately 10 to the minus 4th molarity. And that means that delta G for this, under standard conditions, is about 23.9 kilojoules per mole. So these values might imply the reaction does not proceed effectively as drawn from reactant to product as written. However, the reaction makes 2 molecules. It's making glyceraldehyde 3-phosphate and dihydroxyacetone phosphate from a single molecule. And the equilibrium is thus greatly influenced by concentration. So the value of delta G in erythrocytes is actually negative 0.23 kilojoules per mole. In erythrocytes under biological conditions. So at physiological concentrations, this reaction is essentially at equilibrium. And having reactions which are at equilibrium isn't a problem, because we didn't have to invest energy for this equilibrium to take place. So what we can do biologically is we can link equilibrium reactions together, and then if we have one reaction which is highly favorable, either by nature of the chemical reaction taking place or by an investment of coupling to something else, this highly favorable reaction will drag all of those equilibrium processes forward through Le Chatelier's principle. So as long as something doesn't cost anything, which is the case in this particular reaction, having it operating under equilibrium conditions or near equilibrium is perfectly acceptable. So the final reaction in the first phase of glycolysis is going to be converting dihydroxyacetone phosphate to glyceraldehyde 3-phosphate via triose phosphate isomerase enzyme. And that's going to look like this. We've got our dihydroxyacetone phosphate, and it's going to be reversibly interconverted to our glyceraldehyde 3-phosphate. via triose phosphate isomerase. So of these, only glyceraldehyde 3-phosphate goes directly into the second phase of glycolysis. Our other triose phosphate, dihydroxyacetone phosphate, must be converted to glyceraldehyde 3-phosphate through triose phosphate isomerase to facilitate this. This reaction therefore permits both products of the aldolase reaction to continue into the glycolytic pathway, in essence making two equivalents of one product, which is why having that pseudosymmetry in the fructose 1,6-bisphosphate was really so critical, so we could interconvert between the two final products of its cleavage. The reaction mechanism involves an ene-diol intermediate that can either, let's see, do I want to get into this? Instead of really elaborating on the mechanism of the interconversion, I really think what the best case of action for brevity in this video is for you guys to reference the mechanism in your book. It's figure 18.3, and you'll be able to see how dihydroxyacetone moves through an ene-diol intermediate to glyceraldehyde 3-phosphate. And this triose phosphate isomerase reaction completes the first phase of glycolysis. Although the last two steps of the pathway are energetically not particularly favorable, the overall 5 steps of the reaction sequence have a net delta G of plus 2.2 kilojoules per mole under standard conditions. Which is nearly at equilibrium. And it's the free energy of hydrolysis from the two priming molecules of ATP that brings the overall equilibrium constant close to 1 under these Stadler state conditions. Now, the net delta G under cellular conditions is quite negative. It's very favorable at negative 53.4. So make sure we keep those two values separated. But it is valuable to look at these mechanisms and get a sense of how the enzymes are abstracting protons, moving electrons to form high energy intermediates, then undergo rearrangement and give you new products. So I encourage you to get into your book and look at figure 1813 to get a little bit of clarity on the specific mechanism. That said, this is the end of the first phase of glycolysis detail. And what we're going to do is call this lecture here. And then when we pick up the next lecture, we're going to go into the second phase, rationalize the chemical and biological rationale of the second phase, and talk a little bit more about regulation. And that said, I'll be talking to you guys soon.